Hi, this is a video to help you through the activity on pH and pKa's. Every aqueous solution has a little bit of hydroxide and hydronium ion in it. Because water reacts with itself in an acid-base reaction, this reaction is shown in front of you. This is the autoionization of water. It's defined by an equilibrium constant, Kw. The W in Kw just stands for water, and this is a regular equilibrium constant. This is the same equilibrium constant that you were asked to write in the previous activities check for understanding section. This is the Kw expression, or the equilibrium constant expression for the autoionization of water. The value of K is 1 times 10 to the negative 14. This is a very, very small number, and it indicates that this reaction lies far to the left-hand side. In other words, there are very, very few hydroxide ions and hydronium ions in pure water. Most water exists as H2O. This makes sense if you remember our electrolyte demonstration, where we demonstrated that water is not a good conductor of electricity. If there were a significant number of ions in solution, you would expect water to be a good conductor of electricity, or a good electrolyte, but it's not. And so you know from experience that there are not very many ions in pure water. Most water exists as H2O. The value for the Kw defines the range for concentrations of hydroxide and hydronium ion in regular water solutions. The range is from 10 to the negative 14 at the very low end and all the way up to 1 molar. On this diagram, I've written the possible hydrogen ion concentrations ranging from 1 molar to 10 to the negative 14 molar. So this is the hydrogen ion or the hydronium ion concentration in molarity, and this is the high end and this is the low end. This is what we know, or this is the scale that we know as acidity or basicity. This is a strong acid. At very high hydronium ion concentrations, we have acidic solutions, and at very low concentrations of hydronium ion, we actually have higher concentrations of OH-, and these are basic solutions. Today we're going to talk about the concentration of hydronium ion in solutions using pH. The reason we use pH is because it's hard for us to think of concentrations in terms of exponential values. And so we use a logarithmic scale instead. The logarithmic scale is the pH scale. P just means that it's the negative log of something, and the H stands for hydrogen ion concentration, which is the same as hydronium ion concentration in water. All of the solutions that we will discuss are aqueous solutions, or solutions in water. The pH is therefore equal to the negative log of the hydronium or the hydrogen ion concentration. Anytime you see a P in front of something, expect that it's the negative log of that thing. I can rearrange this equation to give another form that's useful if I'm trying to find the hydronium ion concentration given the pH. Make sure that you know how to do these kind of conversions using your calculator. If you try to find the pH of a solution that has 10 to the negative 7th molar hydrogen ion concentration, you should get the pH is 7. Practice with your calculator and make sure that you understand the conversion between the hydronium ion concentration and the pH. If you need help, ask a friend or come find your professor. I'd like to point out something very simple but very important. This is the hydronium ion concentration, and at this end of my scale, I am at the highest end of the concentration scale. On the other side here, I'm at the lowest end. But when I'm talking about pH, a high acid concentration gives you a very low pH number, and on the other hand, a very low concentration of hydrogen ions gives you a very high pH number. There is an inverse relationship between the value and its negative log value. Acidic solutions have high concentrations of acid, but very low pH. On the other hand, basic solutions have very low concentrations of acid, but high pH values. Make sure you take a moment to understand this inverse relationship. If it helps you, have a diagram like this in front of you as you're answering questions in the rest of the activity. Now let's practice with some calculations using the equations right here. Notice that these equations are written on your activity. It might be a good idea to pause the video now and reread this page of the activity to make sure that the information makes sense before we go on. Please try to do the questions on this page and the following page that give you practice at calculating pH and hydronium ion concentrations. Let's do one together. And I'll point out before we start that there is a new rule that you'll need to learn for logarithms when we're talking about significant figures. This is a different type of manipulation than we've done before. And it turns out that the decimal places in the pH value will be equal to the total significant figures in the hydronium ion concentration, or vice versa. The total significant figures in the hydronium ion concentration will be equal to the decimal places in the pH. Write this down and use it as reference when you're doing calculations like this. To calculate the pH of pure water, if the hydronium ion concentration is 1.0 times 10 to the negative 7th, we'll use the formula that pH is equal to the negative log of the hydronium ion concentration. Here, if I plug in the hydronium ion concentration, I can get my pH. Notice that I'm going to need to pay attention to the significant figures in this number that I was given, because it's the hydronium ion concentration. The total sig figs here is 2. And so I should have 2 decimal places in my answer for pH. Now let's try number 2. In 2a, it's asking what the hydronium ion concentration is based on a pH of 4.1. Here I'll use the equation that the hydronium ion concentration is equal to 10 to the negative pH. The pH here was 4.1, and my answer ends up being 7.95, and etc., times 10 to the negative 5th. Giving this in the right number of significant figures means that I have to pay attention to the decimal places in the pH. Remember, decimal places in pH must equal the total sig figs in the hydronium ion. So here I had only 1 decimal place in my pH, and so I have to round in my hydronium ion concentration for a final answer in the correct number of significant figures. Now this problem tells you that acidic solutions have hydronium ion concentrations greater than 1.0 times 10 to the negative 7th. If you look at the pH scale that I showed you on the first page of the activity, notice that it ranges from 0 to 14. You may know from experience that pH 7 is neutral. This is the same as saying a hydronium ion concentration of 10 to the negative 7th is neutral. And anything greater than this number, so more acid than neutral, means it's acidic. So it might be easy to answer this second question, part B here, looking at either the pH or the hydronium ion concentration. This solution is acidic because its pH is 4.1, it's below 7, and the hydrogen ion concentration is greater than 1 times 10 to the negative 7th. Please check the key to make sure that your other problems are correct and that you're reporting your values in the correct number of significant figures. Now let's talk about pKa's and Ka's. In front of you, I have a generic acid dissociation equation. This is the reaction of a generic acid with water. The acid will lose a proton and become A-. The water will act as a base and it will pick up the proton that is lost by the acid. So water will become hydronium ion. This is a generic acid dissociation equation. Its equilibrium constant, K, is often represented by Ka, where the little a stands for acid. This is still just a regular equilibrium constant. On your activity, there is a table of Ka and pKa values for substances that are weak acids. Here is a list of the weak acid name, their formulas, the pKa's, and the Ka value. Let's talk about the meaning of the Ka value in terms of acid strength. The more hydronium ion that is produced by a weak acid, the stronger that this acid is. In other words, the larger the Ka value is, the stronger the acid. Because if this Ka value is larger, it means that the reaction lies in the more forward direction. So there's a relationship between this Ka and the strength of the acid, because the bigger the Ka value, the more hydronium ion is produced. And the bigger the Ka value, the stronger this acid. Notice that these acids are arranged by order of Ka value. The exponent on these values is the most important thing that tells you the relative size of the Ka value. This table is arranged from high Ka value to low Ka value, or from strong to weak acids. The strongest acids are at the top of this chart, and the weakest acids are at the bottom. Also listed is the pKa value. The pKa value, just like a pH, is the negative log of the value. So pKa is the negative log of the Ka value. Notice that this pKa is just the negative log of this Ka value, and so on. You could plug any of these Ka values into this equation and you should find the pKa value. Notice that the larger Ka values are at the top of this table, but the largest pKa values are at the bottom of the table. Once again, there's an inverse relationship between the negative log and the value. I have smaller pKa's at the top and larger pKa's at the bottom. I have larger Ka's at the top and smaller Ka's at the bottom. A strong weak acid will have a larger Ka value or a smaller pKa, whereas a weaker weak acid will have a smaller Ka and a larger pKa. Make sure you record these relationships on the page of your activity. These inverse relationships are hard to wrap your brain around, so make sure you spend some time right now, pause the video if you need to, and let this information sink in. Analyze the data in this chart and make sure you understand these relationships. You can test yourself by answering the questions on this page. Please pause the video and reread this material, make sure it makes sense, answer the questions before you move on. Now let's talk about the relationship between the pH and the pKa. We use the pH because it's easier to think of than these exponential values of hydronium ion concentration. And we use the pKa because it can be mapped right onto the pH scale, and it can tell you about the forms of an acid that are present at any pH of solution. I want to stress that pH and pKa are related because they're both negative log values, but pH specifically refers to the amount of hydronium ion in a solution. pKa is specific for a given acid. There's always one pKa value for an acid. This is acetic acid. Here is the acid and conjugate base form, and shown here is the acid dissociation reaction. Here I'm simply showing the dissociation of a carboxylic acid to its carboxylate and hydrogen ion. I could have also written this as a reaction of water plus the acid goes to the base plus H3O+. Both things mean essentially the same thing. This is my acid and my conjugate base form. The pKa of this acid is 4.76. The pKa value of an acid can be used to determine what form of the acid is present in solution, the acid form or the base form. I'm going to map my pKa value onto my pH scale. This is the pKa of this acid on the pH scale of a solution. When the pH of a solution is equal to the pKa value, so if my pH were 4.76, there are exactly the same concentrations of the conjugate acid and conjugate base form of this structure. Whenever the pH is equal to the pKa, there are equal amounts of acid and base in solution. But what happens at pHs that are not the same as the pKa? What if we were at a pH of 2 or 1? These are acidic pHs. As I change a pH from 4.76 to a lower pH, essentially what you're doing is you're increasing the concentration of hydronium ion or hydrogen ion. So if I move to a pH that's lower, that means I have a higher concentration of hydronium ion or hydrogen ion. Consider what this would do to the equilibrium. If you started out at 50-50 and you added more hydrogen ion to solution, which way would the equilibrium shift? And which one of these two things would be the most concentrated in solution? If you said that an increase in the hydrogen ion concentration would shift the equilibrium to the left, you're right. And that would decrease the concentration of the basic version of this and increase the acidic version. This is true for all acids. At any pH that's below the pKa of this functional group, the acidic form of the conjugate acid-base pair will predominate, or it will be a higher concentration in solution than the base. The opposite is true if the pH is above the pKa. If I was at a pH above the pKa, that means that I would have less hydrogen ion in solution, or it's the same as taking away hydrogen ion from this equilibrium. Which way would the equilibrium shift, and which form of acetic acid would predominate? If I started out at 50-50 and I removed hydrogen ion, I would shift the equilibrium to the right and I would have more of the basic form than the acidic form. Anytime you have a pH above the pKa value, the basic form will predominate for that particular acid. Please take a moment to write down which structures of acetic acid would predominate in solution at the pHs that are given on your activity: pH 2, pH 4.76, and pH 10. At pH 2, the acidic form, or this form, would predominate in solution. At pH 4.7, neither one of the forms would predominate, and they would be equal. So you would have equal concentrations of the acidic and basic forms. However, at pH 10, you're above the pKa, and so the basic form of this conjugate acid-base pair would predominate. Okay, make sure you get this stuff because we're about to make it a little more complicated. On the next discussion, I'm going to be using the same principle, but I'm going to apply it to a situation where I have two functional groups to worry about at the same time. Essentially, at the very fundamental level, this is exactly the same thing, but now I'm going to worry about two functional groups instead of just one. Amino acids are the building blocks of proteins, and we're going to learn more about this in the semester. But for now, I just want to look at individual amino acids and their characteristics. Alanine is one of the simplest amino acids. All amino acids have at least two functional groups, and they'll all have a carboxylic acid functional group and a protonated amine. The forms of these two functional groups can change though. There are conjugate acid and base versions of each of these functional groups, and they will change depending on the solution pH. The carboxylic acid has a pKa of 2.3, and the amine has a pKa of 9.7. Ask yourself right now, which one is more acidic? The carboxylic acid is more acidic because it has a smaller pKa value, which means it would have a larger Ka value. And the amine is less acidic because it has a larger pKa value. Okay, now let's map these two pKa values onto our pH scale just for reference. First, I'm going to focus only on the carboxylic acid. And if you compare this part of the activity to the one that we just did, it's exactly the same. This is a carboxylic acid, and it can change into a carboxylate, just like it did on acetic acid. Here I'm going to circle the carboxylic acid or carboxylate functional groups. Notice that there's no change from here to here. The only change is from a carboxylic acid to a carboxylate. And this change will happen around this pKa. So remember, where the pH is equal to the pKa, you have 50-50 of each of these conjugate acid-base forms. The carboxylic acid is the more acidic form, and the carboxylate is the more basic form. At acidic pHs, where the pH is lower than the pKa, you would expect the carboxylic acid to predominate. At pH 2.3, there would be equal carboxylic acid and carboxylate, but above pH 2.3, the carboxylate would predominate, and you would form more and more of the carboxylate the higher the pH becomes. Okay, so that's for the carboxylic acid. Anywhere where the pH is below the pKa, you would expect the carboxylic acid to predominate, and everywhere where the pH is above the pKa, you expect the carboxylate, or the conjugate base version, to predominate. Notice I haven't considered the amine in any of this, because the amine is a separate functional group. It has the same types of rules, but its pKa is different, and it's right here on the pH scale. Let's focus only on the amine now. And notice that there are two versions of the amine. There are the protonated amine, which is shown on these first two structures, and then the protonated amine can change into the regular amine. Both of these are primary amines. This one is protonated. The protonated form is the conjugate acid, and the unprotonated form is the conjugate base. When the pH is equal to the pKa at 9.7, you would have equal amounts of these two functional groups in solution. At pHs that are lower than the pKa, you would expect to have the conjugate acid form of this particular functional group. So at all of the pHs below the pKa of the amine will be protonated. And at all the pHs above the pKa, the amine will become deprotonated, and the amine itself will predominate in solution. After you've mapped these things onto a pH scale, it's very simple to tell which forms of the amino acid will predominate in solution. When the pH is lower than both of the pKa's, both of the functional groups will exist in their acidic form. So the carboxylic acid form will predominate and the protonated amine will predominate. At the pHs that are below both of the pKa's, I will see the alanine cation, where both of the functional groups are in their acidic form. On the other hand, if I'm at a pH that's above both of the pKa's, I will have both of the functional groups in their conjugate base form. So if I was at pH 12, I would have the carboxylate functional group and I would have the regular unprotonated amine. I would see the alanine anion predominating in solution because this is the version of this molecule that has both of the base forms of the conjugate acid-base pairs. However, if I'm in the zone in between the two pKa's, anywhere in this zone, I am above the pKa of the carboxylic acid. So the carboxylate functional group will have formed this. But I'm below the pKa of the protonated amine. So the protonated amine will not have been deprotonated yet. So anywhere in this zone between the two pKa's, I will find the alanine Zwitterion, where the nitrogen has a positive charge and the carboxylate has a negative charge. This is the form of an amino acid that is present at neutral pH. Remember, neutral pH is pH 7. The dominant form of every amino acid is its Zwitterion, where it has a carboxylate functional group and a protonated amine. Some amino acids have an additional functional group on its side chain. We'll save that part of the discussion for next time. Now, neutral pH is pH 7. And in this zone here, I have the Zwitterion as the major species in solution. If I start at a very acidic pH, I would have the alanine cation. And as I would raise the pH by adding sodium hydroxide, for example, I would raise the pH and I would start converting some of the alanine cation into the Zwitterion because I would deprotonate the carboxylic acid into the carboxylate. So as I increase the pH, I decrease the amount of the cation and I increase the amount of the Zwitterion until I reach a pH that's equal to the pKa. At this point, I have equal amounts of the cation and the Zwitterion. As I continue to increase the pH, now I'm converting more of the cation into the alanine Zwitterion. I will continue to do this until I'm 100% of the Zwitterion in solution. This is the point when the pH is equal to the average of the two pKa's, or you're halfway between the two pKa's here. This point is called the isoelectric point. It's represented as Pi. The Pi is where the pH is equal to the average of the two pKa's, or if there are more, it's the average of 3 or 4 pKa's. And for this amino acid, it's the point where the Zwitterion is the only thing in solution. So as we move from here to here, we're increasing the amount of the Zwitterion and decreasing the amount of the alanine cation until we reach this pH 6, which is the average of the two pKa's, the isoelectric point. Now I have 100% of the Zwitterion. Now, as I move to even higher pH, I start converting the Zwitterion into the alanine anion because the amine is beginning to be deprotonated. The amine is beginning to react. I will produce more and more of the alanine anion and less of the Zwitterion as I move towards pH 9.7. When I am at the pH that's equal to the pKa of the amine, then I will have 50% of the Zwitterion and 50% of the alanine anion, or 50% of the protonated amine and 50% of the amine. Notice that there's no change in the carboxylate functional group because it's already in its conjugate base form. So here I have 50-50 of the Zwitterion and alanine anion. As I continue to increase the pH, I will continue to make more of the alanine anion until at some point the alanine anion is 100% of the species in solution. Okay, just to review, any point below both pKa's will have the conjugate acid forms of all of those things. Any point above both pKa's will have the conjugate base form. Anywhere between the two, we have the conjugate base of one of the forms and the conjugate acid of the other functional group. pH 7 is neutral, and the isoelectric point is the place where there's 100% of the zwitterion, and that is halfway in between two pKa's, or it's the average of pKa's, especially when there's more than two pKa's to worry about. Okay, please practice with this information. Make sure you can complete the information in your activities and check the key to make sure that you're correct. Thanks for watching this video on pH and pKa's. If you have any questions, feel free to post them in the comment section and let me know if this video was helpful.